Welcome to hi and welcome to track C of Data Summit Connect. I'm MariaDB Ojala and I am your conference program director and moderator for this track. We have two presentations in this session. We will be starting off with Guy Harrison, who is the CTO of Southbank Software and a columnist for database trends and applications. Following Guy will be Rob Hedgpeth, who is a developer evangelist with MariaDB. If you have questions for either of our presenters, do put those into the chat box. We love questions. We actually have answers. So let's get started with Guy's presentation. Go ahead, Guy.
Hello, I'm Guy Harrison, and this is the presentation, Next Generation Databases. It should take us about half an hour to go through the content. There'll hopefully be a bit of time for questions. So just to introduce myself, I'm the CTO at ProvenDB. I'm also a columnist at Database Trends and Applications. I've written a fair few books on database technology over the decades. This particular presentation is based on my book, Next Generation Databases, that you can see there. I've basically been working in database technology all of my professional life, coming all the way from the mid-80s through to today. So hopefully I've got a reasonable perspective. I'm the CTO of a blockchain database company, ProvenDB, partner at Toba Capital, and you can reach me at email on the web there at guyharrison.net. And there's my Twitter and LinkedIn handles. So please feel free to reach out if there's any comments or questions about this presentation. So next generation databases is really, in some respects, a talk about three revolutions in database technologies that I've seen, at least over my lifetime. And so if we look at the history of databases, databases existed probably before computers in some form. We had punched card systems, arguably a library is sort of a database in a building with indexes and organized collections of databases of data. But we really start to think about databases with the invention of the magnetic tape and magnetic disk. There were databases in the 60s, late 50s and 60s based on various models working on mainframe technology. But in 1970, Edgar Codd invented the relational model or proposed a relational model for the storage of data. And a short while after that, all of the databases that were produced over a period of 20 years were relational databases. They all used a relational data model, the SQL language, and ACID transactions. But then about 10 years ago, we saw a sudden burst of new database systems, and almost none of those followed the relational model. They were all based on NoSQL, big data, other technologies that we'll talk about. So why have we seen these three different waves of database systems? Well, the simplest way I can think to talk about it is that we've seen three waves of application technology. The first waves of applications ran on the mainframe, all self-contained in a single platform. They had millions of users worldwide only. The second revolution came about during the era of the mini computer, the PC, the client-server platform. Hundreds of millions of users worldwide, revolutionized business, but still didn't reach the everyday person. And then the third revolution was essentially triggered by the internet, but included other things like social media, big data, mobile devices, and so forth. And at this point, billions of users, millions of apps. Now, this third wave of application required global scale, the ability to send an application to the entire world with essentially no downtime, and transaction rates and demands on data volumes that simply couldn't be met by the relational database. And this is essentially why we saw this explosion of new systems about 10 years ago. And so we can look at a few major trends that led to these explosions. And we'll do that in the next couple of slides. So the first one I want to talk about is big data, or another way of talking about that might be the industrial revolution of data. It used to be that an organization's data was created internally. There was literally people punching data into data punch operators, into data capture devices. But as we know today, an organization gets its data mostly from outside. It comes from everywhere. And one illustration of how everyone's become a creator and consumer of data, or the one I like, is to look at the Sistine Chapel in 2005. A new pope was about to be announced, and you can see everyone sitting there waiting patiently. And there we see, you know, maybe one person's on some sort of mobile device. Fast forward 2013, another pope is announced, and now everybody is recording and producing and consuming data. Literally everyone seems to be connected to the internet. And it's not just people. Everything that can be connected to the internet is connected to the internet. And all of these things are creating and consuming data at ever increasing rates. Now, the first company that really had to deal with the amount of data being created by the internet was Google. Right from the start, Google had to deal with exponentially growing amounts of web pages that they needed to index. When Google started, they used a hardware platform, which was essentially just servers under a desk, and this is literally Google's first hardware platform. And they soon moved to more traditional, you know, rack-mounted servers. But even that sort of architecture became insufficient. And so around about 15 years ago, Google moved to consuming servers in container loads. And so this is a shipping container with its own dedicated power supply, air conditioning. Inside this shipping container, there are tons of servers. They're always failing. So this guy's come in to sort of pull one in and push one out. They're not failing because they're fallible. They're just failing because there's so many. You know, you can't expect these millions of servers to sort of like all keep working. And so in a Google data center, what you see is shipping containers of servers, you know, loaded up. When you and I might think of buying a new computer, Google thinks about getting new shipping containers full of computers. And this is still staggering to me, even 15 years later, the sheer scale and ambition of Google's hardware platform. And this hardware platform demanded a new type of software platform. And Google described how they'd created a thing called Google File System, an algorithm called MapReduce. And the open source community saw this and copied it into a thing called Hadoop. And Hadoop was essentially an open source implementation of Google's algorithms. Now, Hadoop caught the attention of Yahoo. At this point, Yahoo was still trying to compete with Hadoop, with Google, sorry. And so they implemented Hadoop at scale. And so Hadoop got very battle tested very early on for an open source technology. And as a result, when it was released to the world, it was rapidly adopted by a lot of top tier companies. And the idea here was we were heading towards a new era of big data and a new type of data store called the data lake. And the data lake would just be a Hadoop type system in which we could throw all our data into this massive data store. And we'd use machine learning and dashboard and analytics to derive value from that data. Now, of course, it's a lot more complicated than this diagram. So people started developing, you know, data lake reference architectures. And in fact, it's a lot more complicated than this diagram. So we get more and more things in the data lake. We get more and more components, more and more moving parts. And after a while, the data lake, which was, you know, imagined as this pristine area of pure, beautiful, drinkable data, turned into a data swamp, an area of data which is stale and hard to use and hard to navigate. And so this whole ideal sort of fell apart for three main reasons. First off, Hadoop turned out to be very slow. It was scalable, but it just wasn't fast enough for the sort of like the fast moving analytic demand of the modern era. Hadoop was great for dropping data in without sort of bothering to define it, but that created a whole lot of difficulty around, you know, knowing what was in there, what we call metadata, data about data. There were a shortage of people who could leverage the data stored in Hadoop systems. And when we all started moving to the cloud, there are a lot cheaper alternatives than Hadoop. And so really Hadoop thrived during the 2010s, but sort of by the end of the 2010s, it sort of failed as people were moving into the cloud. And so what we did see, though, is we saw a return of a SQL data warehouse, in particular Snowflake, which is a cloud-native SQL database that can work with all sorts of different data sources like Hadoop, but which still supports SQL, and which was specifically designed to work inside cloud organizations or cloud infrastructures, scale out on demand, became very popular. And when they IPO'd last year, it was the biggest IPO of all time. So obviously there's a lot of momentum behind this now, and we can sort of see this having closed full circle. Hadoop threatened the SQL data warehouse on premise. Ironically, it was the SQL data warehouse in the cloud that was the final nail in Hadoop's coffin, arguably. Now, the other trend besides big data that I'd like to talk about is NoSQL. Or when we say NoSQL, we don't mean NoSQL. So you'll see what I mean by that joke in a minute. But to understand where NoSQL comes from, we have to sort of wind back to how applications were built in the early era of the internet. Now, typically what you'd have is you'd have a web server that, we all know what a web server is. It serves up HTML to consumers on web browsers, and it would attach to a database where the data that drove the content of the web pages lived. And if you got too sort of much load for that one web server, you could easily add more. And if your database got overloaded, you could sort of start using caching servers. If that still didn't work, you could start replicating the database into read-only slaves. But if the write activity, that single database server got too much, what most companies did, or what companies like Facebook and Twitter did, was shard, which is to split up the database into multiple chunks. So at Twitter or Facebook, you might find that there are thousands of shards, and each shard holds data for an individual person. So my data might be in shard 2, your data might be in shard 1, and the application needs to know how to talk to all these shards and all these replicas to get all this information. Now, this is a very complicated architecture at this point, and we've kind of broken all of the ability of the SQL database. We can't do joins anymore. We can't do transaction. Furthermore, we still haven't solved one of the core problems that was facing the web in the early days, which is what happens when there's a network partition. So what happens if you've got data in the US, or you've got customers in the US and you've got customers in Australia, and they're working to local data centers connected by the internet? All's well, and both, if I'm Amazon, I can sell in Australia and I can sell in the US. But if there's a network partition between the US and Australia, what happens? Well, in the model of databases as they existed in the early 2000s, Australia would essentially be cut off, or at least go read-only. You wouldn't be able to buy anything in Australia. And Amazon really didn't like this idea. They wanted to keep going, even in the event of a network partition. So they invented a new type of database called Dynamo, which was eventually consistent, which let these two data centers operate continuously, even when they were cut in two. I don't want to go into too much detail about Dynamo technology, but effectively in Dynamo, you have all of your data split up into multiple servers. And when data is written to one of those servers, it's instantaneously or asynchronously, depending on how you configure it, written to other nodes in the cluster. And those nodes can be in a different rack or a different data center. So you can arrange for your data to be spread across the world. And none of these nodes are particularly master nodes. So any of these nodes can serve up reads and writes. And so if it's split in two, it can still keep operating. Now, there were a lot of Dynamo-based databases that arose after Amazon pioneered this. A few of them here: Cassandra, React. React's gone now, but Cassandra and Scylla are still around. And of course, DynamoDB is Amazon's own implementation of Dynamo that you can consume on the Amazon cloud. Now, this was all very well, but this eventual consistency led to a lot of problems in terms of not being able to have true transactions and getting data inconsistencies that a lot of organizations found difficult. So Google had to think about this and tried to come up with a different model. And they said, what, instead of giving up consistency in the network, what if we tried to eliminate network partitions as much as possible? And all of the inconsistencies arrived from having data spread across the whole world. And how could they do that? Well, they used their own highly redundant internal network and onboard atomic clocks to make sure that the idea of time across the world was always the same. and that there was very little chance of networks going down. So we talked about network partitions before. Well, if you're Google, you've got such a strong network with so much redundancy that a network partition seems fairly unlikely. Still might happen, but it's so unlikely that you don't really need to engineer around it. You can sort of live with the chance because the chance of it is so low. And at the same time, in each of these data centers all around the world, atomic clocks and GPS devices allow for each server to have a very, very precise idea about the sequence of transactions. Even if the transaction happens in London and New York, we can work out which one came first, and therefore we can sequence them correctly in order to avoid any inconsistencies. Now, Span is only available within Google's own network, but it has created a lot of, if not copies, but databases that are inspired by this idea. And we've come back from the NoSQL database to the distributed SQL database. The most well-known one is CockroachDB, which is doing extremely well. TiDB and UGLbyteDB have very similar ideas, and they're both sort of continue to embrace the SQL language, ACID transactions, but are able to sort of solve this distributed data at scale. Now, another thing that these distributed SQL databases, these new breeds of databases are good at, is working within containerized environments and in Kubernetes. And to understand, if you're not familiar with Kubernetes, I'm going to give you a very brief sort of like explanation of what it is and how it fits into the current application landscape. Again, to do that, we need to go back in time and see how things have evolved. Now, in the first iteration, that first wave of applications, the application of the database sat in the same physical machine. And then we moved to client server, in which the application logic was on a client, like a Windows PC, and the business logic was on a server, and perhaps an Oracle database running on VMS or some Unix system. The internet took the client server architecture and initially didn't change it very much, just added the web browser. Over this century, we've done a lot of work on virtualization, where we place all of the components of an application inside virtual machines, and we can put them all in virtualization servers, which allow us to effectively share hardware and give us some scaling advantages. But it's still essentially the client-server architecture with a little bit of a tweak. But over the past 5 to 10 years, most significant organizations have moved to a microservices architecture and containers. Microservices mean we no longer think of the application as being one monolithic block of code that has to run on one machine. We break things up into little services that can interact in useful ways that can run anywhere. And running anywhere can be achieved very easily with Docker, which is like a very lightweight virtualization solution that you just run one microservice in a Docker container. And Kubernetes allows you to coordinate the implementation, the failover, the load balancing of all these services. But up until recently, databases have not been able to fit inside this lovely Kubernetes orchestrated environment. They've been too monolithic. They don't break up easily. They don't scale well. So you typically, in early Kubernetes environments, the database would be left outside. But these new breed of distributed SQL databases work very well with Kubernetes. They're able to split up their load across multiple nodes. And I should say that the same is true of Dynamo-inspired databases like Cassandra. These are databases that do not have one big monolithic database server that can't be placed in a containerized environment. But the future of application infrastructure at the moment appears to be Kubernetes. And as a result, these new generation of databases have a huge advantage over the older generation of things like MySQL and Oracle and so forth. Now, the third factor, or another factor that influenced the development of database technologies was developers, or the mismatch between the object orientation and the relational model, or the battle between continuous integration and alter table. Now, developers had always disliked SQL. The idea that you took a lovely object-oriented model and had to break it apart into multiple tables was like having a car that you had to disassemble and place into little drawers when you drove it home and reassemble it each day when you drove back to work. You'd have an object, a programming object, that had a lot of well thought out structure, but the relational model insisted that you break that up into multiple tables. It's also true that SQL statements in most programming languages are hard to write and hard to test and hard to maintain. And fixed schemas work against agile development and continuous integration. If you have to have a DBA approve an alter table statement to a database, then you can't have a continuous integration workflow that involves any sort of schema changes. And as we move to agile, continuous integration, DevOps, this tension became increasingly difficult to resolve. So as a result of this tension, document databases became enormously popular in the last 10 years. And in a document database, instead of decomposing data into tables, you'd store everything in your object as a JSON document that would usually map pretty directly to the object that was in the program code. So here you see an example of a JSON object on the right, the alternative of breaking it up into 3 tables on the left. MongoDB is the most popular document database. It's been the fastest growing database in the past 5 years overall. It's got a huge amount of developer activity. And it's of the top 5 databases by most reckonings, it's the only one that has its technology origins in this century. So in a way, it's the most popular modern database of all. But it's probably worth noting that all the SQL databases now natively support JSON, so JavaScript object notation. So Oracle, SQL Server, Postgres, Azure Cosmos DB, it's all possible in all of these databases to store data within the relational database as JSON. And at the same time, all of the NoSQL databases have created some form of support for SQL because SQL is so popular. So we may see that these two trends, this sort of NoSQL document database versus the SQL traditional database, actually merge into something that's really just a smaller differentiator than it currently is. So we haven't really talked about cloud yet, and obviously cloud is one of the most important factors in database technology. Cloud databases have hit a tipping point in the past few years, or to put it another way, Larry was wrong. So Larry Ellison famously in 2009 said that the cloud was nonsense. It was gibberish, it was insane, it was idiocy. And he had something, there was something there in what he was saying at the time, because databases and the cloud didn't work well together at that point. Because if you moved your database into the cloud, you would open it up to the outside network, which was a security issue, and you increase the network latency between the application and the database. So simply moving databases into the cloud wasn't a very good idea, and pretty much no one was doing it, while applications continued to mainly exist on-premise. But once applications moved into the cloud, this difficulty just went away. And as you would be well aware, most applications are in the cloud already now. So increasingly, as organizations are moving their application stack into cloud, they're moving their databases in there at the same time. And we can see cloud databases are the fastest growing category of database in general. Things like Snowflake DB and a Cockroach DB that we talked about are growing really, really fast compared with the traditional databases. And all of the traditional databases are in the cloud first anyway. Things like MongoDB and Oracle did not start in the cloud, but now their cloud offerings are very important to them. So a few more topics to go. Firstly, I just want to talk about convergence, or we might call it the Empire Strikes Back. So we just mentioned Oracle. Back at the Death Star, that is what I affectionately call Oracle HQ. The emperor of databases, Larry Ellison, was very aware of all of this NoSQL, big data, document database stuff going on, and wanted to fight back. So Oracle's consistently been trying to add to its database system everything we've talked about. They have a big data appliance, which is Hadoop in a box. They have JSON support within the database. They have a graph database system, a NoSQL database. They do sharding. And as we just mentioned, they're going into the cloud very aggressively. However, they've really, over the past 10 years, managed to lose the developer community quite remarkably. You see here on the Stack Overflow survey, Oracle's the second least loved and the second most dreaded database system. And unless they can overcome this developer distaste, I don't personally see what they can do to be part of the next generation of database systems. Microsoft's another company that's trying very hard to bring everything into one platform. You can see here that Azure Cosmos DB supports a lot of the things we've been talking about. You see Cassandra up there, JavaScript, object notation, MongoDB. They support graph database models. They have eventual consistency and strict consistency. So it tries to be everything to everyone. And it has a sort of a spanner type high availability model. Very impressed with it personally. They're not, I think, growing as fast as some of the other database platforms, but they're definitely one to watch. And the final topic I wanted to talk about was blockchain. Blockchain is a unique paradigm shift in the way we think about data. So just to go back in history a bit, we used to store data, and this is a 10,000-year-old cuneiform clay tablet with some agricultural data on it, so it's like accounting data. We used to store it in physical media, so clay tablets, stone, paper for most of the last millennium. And these media seem primitive today, but they had one advantage, which was they were sort of hard to mess with without leaving a trace. If I went to try and write into something in that ledger, it would be difficult for me to do it in such a way that it couldn't be detected. But ever since the invention of the magnetic disk, and this is the first 5 megabyte magnetic disk, which used to weigh literally a ton, magnetic disks has got faster and cheaper, and of course we've moved to solid state disk. But anything written to a magnetic disk can be overwritten without leaving any sort of trace. And so our entire financial infrastructure is written on a medium that is completely corruptible. And databases themselves cannot really be trusted. And we've seen this in many, many instances of tampering, hacking, falsification of records, and so forth. Now, blockchain, for reasons that I don't have time to talk about now, is a completely trustworthy, immutable data store. And we can be sure on a public blockchain that when we write something, that no one else has been able to overwrite it. That if it says it was written 1 year ago, that was what was written a year ago, and we can't change it. But compared to traditional databases, blockchain is just too slow, has a limited storage capacity, doesn't have proper security, doesn't have a schema or data model, is expensive to run and hard to develop with. And so we have a dilemma at the moment where blockchain seems to be the right thing for immutability and tamper detection, but it just doesn't have the performance and economics. And so when people are constantly asking, should I use a blockchain, should I use a database? And most of the time, the right answer is to use a database. But nevertheless, there are some blockchain databases that offer a sort of a merge between traditional technology and blockchain. My company, ProvenDB, is one of those companies. So here's us. Other companies include Amazon with QLDB, a few other contenders. And we are seeing blockchain capabilities being introduced to databases like Oracle and SQL Server. And so it seems to be one of the next waves of technology that are going to affect database systems. Okay, well, that was a bit of a whirlwind tour of database technology. I know that I've sort of skimmed over a lot of complexity and probably left you wondering about a few things. Obviously, my book, Next Generation Databases, goes into a lot of detail about this. You can find out a lot more if you look at my database trends and applications articles, or go to guyharrison.net and follow from there to my blog and other areas and other resources. So I hope that's been useful. Please let me know if you've got any questions. If you want to reach me, navigate to guyharrison.net. Drop me an email at guy@provendb.com or talk to me on Twitter at @guyharrison. Thank you very much for your time, and I hope you have a great conference.
Thank you so much, Guy. That was quite the whirlwind tour there. Wow, I'm breathless. So let me move on to Rob Hedgpeth, developer evangelist with MariaDB. So Rob, go ahead.
Oh, sorry, there we go. Sorry, I lost my mute button. I My mouse quit today, so I'm like working off of a trackpad and I had to open my laptop and it got kind of crazy. Well, my name is Rob Hedgpeth, as MariaDB said, and I am taking the next session here where I'm going to talk about kind of a case study. I mean, after hearing Guy's session, I'm pretty excited. I really love the way that he went through the history of that. And I'm here in the next 10, 15 minutes to talk to you kind of a more specific case of how you can handle modern workloads, a topic that Guy kind of got into with your database as a service, where he talked about databases in the cloud. And first things first, that I do want to talk about is something that is probably pretty basic, right? What is a database? Well, you know, Guy hit on it, the history of it, and a database is a lot of things, but at its core, you can really just think of a database as a bucket, and you're putting something inside of that bucket, and you can walk away and you can come back. But the point is that it persists somehow at the simplest level. Data inside of this thing, this construct, is persisting. Well, if a database is really that simple, which we know it's not, why do you need a database as a service, right? Why do you need a DBAS? Well, unfortunately, for those of us that have been involved using databases, there's a few things that would make us want to abstract away some of the minutia, like having to provision a machine, you know, whether that's locally, on-prem, or even in the cloud, as Guy had mentioned. You have to set up something, right? Even if it's a virtual machine, to be able to put that database on, install, configure, and then, as I said, actually set up the configuration of the database itself. And you got to get in, and every database is a little bit different. And, you know, you have to set different parameters and security settings, as just the three things that I can start to get into on the tip of the iceberg. But I'm not going to bore you with all the things of why you would necessarily want to abstract that away. I'm sure you can probably lead to a train of thought that's like, yeah, definitely, I want to get rid of that. Well, the dream then, if you're thinking about a database as a service, is that, oh, I want to, however I'm creating my solutions on the left-hand side here, I want to, let's say, be able to use that database in a cloud. And I just want to be able to smack this easy button, and I want to, you know, be able to create a database to, whether I'm a DBA and I want to, you know, be able to get away from having to do some of the more system administration things, or maybe I'm an application engineer and I just want to be able to communicate with the data so I can get back to writing my application code. But at some point, all of us want a level of control. So database as a service, really, if we're thinking about it from a dream perspective, gives us just enough levers, just enough knobs and buttons, basically, to be dangerous, but not too dangerous and not have to dive too deep into the database itself. Unfortunately, the reality of that is really not that simple, right? Is that we know, and Guy kind of talked about this as he went through time, that applications have changed. As we've gone through the different eras, with the onset of the internet and mobile devices and even IoT, we're seeing more and more data ingestion or more data traffic come through. And with these types of applications, you know, we start to look towards the cloud, you know, as Guy had mentioned, is something that we could use to help solve a variety of issues. You know, maybe we want a secure place to be able to store our information or propagate our information worldwide. But then we start to have to look at, okay, do we have existing applications? Do these need to go into a particular service provider? Do I need to, you know, be able to communicate from one service provider to the next? And then eventually we get to that database layer where we decide, okay, well, you know, what database do we want? And in some cases, as Guy mentioned, because of the different types of situations that you have or problems that you may need to solve within your application, you may have databases, right? You may have multiple different database types or database vendors, database solutions that you want to use in order to be able to solve the variety of problems that come with your applications. And so it becomes a lot more complex than just some simple, you know, knobs and levers that you may turn within, you know, the cloud environment. So how can we accomplish this? Well, the first thing that we need to look at is this idea of a database workload, right? Being able to pick the right tool, essentially, or database or, you know, solution for the job. And traditionally, that has been something that we have used specialized databases for, right? We may look at something, what we consider a little bit older school, like an RDBMS, We may look at NoSQL now as something new to handle, more targeted problems. Maybe we need something more write intensive. Maybe we're looking to curate data and we need something like a document DB, or any of the other, column family or graph database data models that we may want to use. Maybe we even want to use something like NewSQL or this idea of distributed SQL for handling massive amounts of scale horizontally. And on the right-hand side, as another option, you may even want to consider something as storing your data in a columnar fashion, where you still have this tabular setup, but instead of focusing on the tables and then rows themselves, you're specifically looking at columns of data to handle statistical information or calculations, albeit aggregations on that information. But there's another way, right? Alternatively, you can consider the way that a solution like MySQL or MariaDB, where I work, has solved it by adding in pluggable storage engine or more specialized storage rather than an entire specialized database, just pluggable storage engines that you can use to handle mixed workloads of reads and writes, maybe more write intensive operations, being able to scale distributed manner in broad amounts of information and theoretically growing exponentially forever, or being able to handle analytical information so that you can take a look at maybe billions of records from a historical perspective. Well, if you're using this approach, one of the advantages you get is that you actually get a common layer of a language. So one of the things that's important to know about how databases have evolved is that SQL has actually been gaining a lot of ground here recently. And that's because, well, one, because you can use it on a little embedded database called SQLite, which is everywhere now, right? And IoT and mobile devices. But another really big reason for that is because as SQL is a declarative language, it can be used in a variety of different circumstances, including different types of storage that it can communicate with. And these different types of storage, I won't get into things like a B tree for mixed read-write workloads, or being able to use a log structured merge tree for more write intensive operations, distributed, which I had mentioned before, and even storing things in a columnar format, or quite literally storing columns as the files rather than entire tables as the files as you get down into the IO. The point of this is that you can use this common language to communicate with different storage engines in order to be able to handle these different workloads. And the way that MariaDB has done this is just that, right? So we've got different storage engines, which a couple of these are actually synonymous with what MySQL used, right? So if you know anything about MariaDB, you know that, a couple of years ago or about a decade ago, they forked from MySQL. And the idea behind MySQL is really to have these pluggable storage engines. And since then, MariaDB has been keeping that same trend and added a couple of different pluggable storage engine types in order to handle those workloads, such as mixed read write, the more write intensive operations, having the ability to expand quite literally with the storage engine called expand, using distributed SQL, and then using column store for analytical purposes. Now, what does this have to do with the cloud? Well, as part of this kind of case study or a deeper dive into a vendor, the one that I happen to work for, but certainly not trying to sell you on it, what we've done is we've decided, and I think that Guy actually mentioned Mongo, for instance, had created Atlas, which is their own cloud hosted or their own database as a service. And we've done something similar called SkySQL. And the idea was to take that simple idea of a database, like I mentioned before, and simply put that into the cloud. And currently it's available on GCP and AWS, and working towards Azure. But the idea here is to take the workloads, I guess, strategy, if you will, and move that up to the cloud so that you can use that for a single database instance and not have to go and pick and choose which different database vendors you need across different clouds in order to solve multiple workload problems. And if you were to go into the database, you would see that you have multiple different types of services that you can launch, from the default transactional, your basic row-based, read-write, analytical, column-based, HTAP, in distributed SQL. And quite literally, if we were to take a very fast look at this, and I know I'm running kind of shorter on time here, the difference between row-based and column-based, like I said, is that it organizes things right way down on disk IO into columns instead of tables, so that whenever you run aggregation queries like this select average, rather than looking at the entire table and having to just average a single column, it gets the advantage of being able to look at much less information to be able to have much less memory impact, or sorry, size impact on your disk IO, which of course it causes improved performance. When you get a pluggable storage engine, then you get the ability to both combine row-based and column-based information. So the idea behind that is something called HTAP, or hybrid transactional analytical processing, where you can write condensed or single queries that can combine both row-based storage and column-based storage. And then finally, as Guy had gotten into, MariaDB also just released a distributed SQL model called Expand, which is a new storage engine which handles information to be fully distributed throughout these nodes. And the idea here is that you can both expand or you can scale out whenever you have a higher load or higher demand. And as demand decreases, you could scale in, thus costing much less money, and basically being able to take advantage of the cloud. And this is all built on a Kubernetes API or Kubernetes, and utilizing the Kubernetes API across the different clouds. And just like Guy had said, taking advantage of both the cloud native technology, making these cloud native databases, and then being able to take advantage of storage mechanisms like block storage and object storage that exist in the cloud itself. But seeing is believing. So if you would like to try this out, you can do this for free. There's a $500 credit. You can check out any workload, any cloud at any scale at mariadb.com/skyview. Thank you very much for entertaining my session.
Wow. That was quite a lot to cover. Between the two of you, I think you truly covered the waterfront here. And in fact, I'm not the only person who thinks that. We do have a comment here in the chat. Great presentations and lots of super information. So thanks to both of you. I think we now not only know where we've come from, but where we're going, which is really kind of the perfect segue towards the closing keynote speaker. So do all of you go to our closing keynote speaker, who is John O'Brien. And, you know, Rob, if you have time, you can come over. I know Guy has to go catch a plane. So thanks to both of you. I don't see any questions in here, just the comment. So thanks again to Rob and to Guy. And, you know, take Rob up on his $500 credit offer there. You know, it's not that frequently you get offered $500 for free.
I only mess with free things. So that's why I put it.
Things.
And I feel like that's how every developer is. I want it free before I have to commit to anything.
Guy, did you have any parting words?
No, it's a pleasure to present. It's pretty early my time, guys. I presented from Australia, and as mentioned, I'm about to jump on a plane to New Zealand, so I've got to get going. But yeah, thanks for the opportunity. And if you've got any questions, you know, please shoot me a line.
And we so appreciate you up this early in the morning. So thanks to both of you. And let's all head over to the closing keynote, except Guy, go catch your plane.